Can any one of you please confirm if I am audible?
Good morning, sir. Good morning. Your voice is coming.
Oh, thanks, sir. Thanks. Okay. So let's start today's class. We'll finish up SRS today and hopefully start the downlink control information. I'll teach you the main concepts of downlink control information today, and then we can go to the details in the later part of the week. Okay. So uplink reference. First, let's start with uplink reference signal. Just one minute. Okay. So uplink reference signals. I mean, we were looking at the SRS of our uplink reference signals, sounding reference signals, and we'll just do a quick revision for 10 minutes and then start the other parts, okay? So these SRS are transmitted from the UV to the base station. Of course, they're configured by the base station. They're used for the uplink. In the uplink channel, they are used for the scheduling and frequency resource allocation. Essentially, you find the channel, and based on the channel, you allocate resources in the uplink. Okay, when you have TED, you use the same SRS channels for to assume that the uplink channel is equal to the downlink channel. This is essentially the channel reciprocity. Okay, so SRS channels play a very, very critical role, particularly in the massive MIMO system. So most of the massive MIMO systems are TED. Okay, and in TDD, SRS play a very, very, very critical role. Okay, so they are actually used to understand the downlink channel. So SRS properties, what are the different properties? What are the properties of SRS? So essentially, the number of transmit ports can be 1, 2, or 4. Okay, so maximum 4 antennas on the uplink. So you can also transmit in 1, 2, or 4 symbols. So SRS is only transmitting the last 6 symbols of a slot, and the transmission can be over 1 symbol, 2 symbol, or 4 symbols. Okay. In the frequency domain, there are 2 combs. One is called the density half comb, and the other is the density 1/4 comb. So density half means every other RE, you have an SRS symbol, SRS pilot, and density 1/4 means you have an every fourth RE, you have a SRS pilot. Okay. So is this clear? Does this make sense till now? Okay. So we have also seen this part till this point. We have seen. So SRS sequences, I mean, so this is the difference between SRS and CSIRS, one of the fundamental difference. So CSIRS actually uses QPSK signals as pilots. Yes, QPSK signals with code division multiplexing or something as pilots. SRS, on the other hand, uses Z-OFF sequences. The main reason is the PAPR in the uplink. Okay, they want to keep it low, so they just stuck to the ZC sequences. So how do they keep them orthogonal over different ports? They can keep it. They can make them orthogonal by looking at the cyclic shifts of these Z-OFF sequences. We have seen this earlier when we were doing PRAS, that you take a Z-OFF sequence, you cyclically shift it. Both the sequences are orthogonal. Okay, so they use the same properties here, and they actually send different cyclic shifts in different ports so that they become orthogonal. Okay, so the number of cyclic shifts and other things are fixed. So in a comb size 4, 12 cyclic shifts are available. In a comb size 8. In a comb size 2, 8 cyclic shifts are available. Okay. So the multiple uses of the cyclic shift. Either you can put multiple ports or you can use multiple UVs on the same core. Either way is fine. I mean, you have to. I mean, depends on your configuration. Okay. So you see the symbol KTC quite a bit in SRS sequences. Okay. So KTC can be either 2 or 4. So that's nothing but the comb size. So you see this KTC occurring all around. Okay. So what is the length of the ZC sequence? For example, how much is the length of the ZC sequence that you will choose? For example, you want the ZC, the SRS to occupy 6 RBs, and you have 2 comb. So you have 6 into 12 REs, and density half. So into half, it's 36 length sequence you have to choose. Okay. Is this clear up to this point? And then we'll now start then. Things that we didn't cover till now. Any other questions till now? Okay. So how are the cyclic shifts done? Just 1 minute. Yeah. So remember this. I'll just come back to the other slide. 1 minute. I'll just show you this. So you want the cyclic shift in the time domain. In the time domain, cyclic shift means in the frequency domain you multiply with a a complex exponential. So this alpha is a cyclic shift. Okay. So how do you choose this alpha? Okay, so alpha depends on a lot of things. one of the main thing that you can see is the cyclic shift. Alpha is proportional. Alpha is equal to 2 pi into NCISRS by NSRS CS max, maximum number of cyclic shifts. Okay, for that particular KT. Okay. Okay, so you see that for different ports, you actually change the cyclic shift. Okay, for different ports you can change the cyclic shift. For example, port 1000 has one cyclic shift, port 1001 will have a different cyclic shift. Okay, so as I told you, the cyclic shift depends on the port number. Okay, so see, remember when we were doing a CSIRS, you kept orthogonality between the ports by using CDM group. So here you are using the cyclic shifts to keep orthogonality between the between the different SRS sequences that you choose. Okay, I'm not going to go into what this is and other things, but you can understand that. See, the main, of course, you can read the very specific things in the spec. So what I'm going to try to emphasize is each port has a different cyclic shift. Okay. So this is the main RRC parameter for this one for the what do you say, SRS. Okay, so you can choose the transmission comb either N2 or N4. In the N2, you can also specify what is the cyclic shift 0 to 7. 8 cyclic shifts are allowed 0 to 7, and in N4 12 cyclic shifts are allowed 0 to 11. Okay, the comb offset is nothing but essentially the offset in the frequency domain. That will come to that later. Okay, so you understood now. So you specify this to the UV. You tell the UV specifically you use this particular cyclic shift. Okay, so. So let's look at the generation of this SRS sequences a bit. So in SRS sequence, one of the generation is, of course, the base sequence is RUB bar, where my cursor is. And this is a cyclic shift. Okay. So the next question is, how do you choose the base sequence? Okay, so base sequence has two parts. One is called, other than the N, which is the length of the sequence that you want, there's something called U, V. Okay, which feed as parameters into the sequence generation and choosing. Okay, so U is called the group number, V is called the sequence number. Okay, so this is something that we will discuss. Okay, so there are 30 groups of SRS sequence. Okay, so what does each group have? So each group contains multiple base sequences. What are the base sequences each group has? A group has one base sequence of all lengths till 60. Okay, it has two base sequences of length greater than 60. Okay, till some number, I don't remember the maximum number, but it has two base sequences of length greater than 60. It's a very large number. Okay, so if you are choosing a sequence less than 60, there's only one base sequence in a particular group, and there are 30 such groups. Okay, and each group has two base sequences if you are greater than 60. The length is greater than 60. Okay, so if specifically for the case when you have two base sequences greater than 60, which base sequence you choose depends on your length as well as this index V is equal to 0, 1. So you always see RUB when they define a Xerox sequence. Okay, U is the group number, B is the sequence number in that group. Okay, and you choose the sequence in the base for the length. If there are ambiguity between the two sequences of the same length, you choose between them using the V, index V. Okay, is this clear? Okay, why do they do this? So why do they have different groups and different? It is different groups. Mainly so essentially what they do is for different cells, for example, they allocate different different groups, so that the interference when there's interference from other cells, it gets averaged out. Instead of using the same base sequence, if you get the same base sequence, maybe you may add up. But if you use a different base sequence and different rotation in a different cell, what might happen is things may get averaged out and the interference may become less. Essentially, mainly to reduce interference and interference. Essentially, what they do is they allocate different base sequences for different cells and different groups for different cells. Okay, that is the main motivation. But one thing you should understand is different base sequences need not be orthogonal. Okay? I mean, need not be orthogonal. Only the shifts of the cyclic shifts of the same base sequence are orthogonal. You will always remember that. Okay. Any question? Okay. So, how do you choose this group selection? Okay, so this is very interesting. Okay, so so there are two ways of choosing this group. One is for a given cell, you keep the group constant. Okay, you keep the group constant. Okay, you fix a cell. Cell means on one base station. You fix the group in which they choose the SRS constant. Other is what they do is they change the SRS group every slot and every symbol. Okay, so that depends on something called the group or selection sequence hopping. You can do one of them. You can't do both. Okay, so if the group or sequence hopping is set to neither, means that don't do any of those. So if you set to neither, of course the sequential group hopping is not used. If the group is set to group hopping, if the IE is set to group hopping, then what happens is every slot and every symbol you change the group. Essentially, you select a different sequence. Okay, so you select a different sequence. So essentially, what happens every time you pick out a different U. Okay, again the main reason is this is mainly to mix out the interference across different cells and across different symbols and slots. Okay, so that the hope is that if you go on changing this at some state, maybe even if there is interference, one symbol or one slot maybe you might be able to decode. Okay. Okay, so you can see this is a complicated function on how you choose your U. Okay, so one is called NID SRS, which is fixed. Okay, so neighboring cells will have different IDs, and this FGH, which depends on the slot number and the symbol number. If you don't do group hopping, this will become 0. If you do group hopping, you have to select that using a formula that depends on the particular symbol number and the slot number and the slot number. Okay, is this clear? Any questions?
Sir, this is not clear. Can you please once again?
Okay.
FGH, the function which
Okay.
decides.
So let me explain you. So we have to, so essentially we know that we are going to send SRS sequences. Yes, we are going to send SRS all the U. So U is multiple UEs may be doing this SRS sequences.
Okay.
Okay. So one thing, the first question is how do you choose this SRS sequence? Okay. So if a particular UV is transmitting 4 ports, then you pick out a base sequence. And the base sequence has multiple cyclic shifts, maybe 4 cyclic shifts that are used across the 4 ports. Okay. Now the question is how are multiple UVs multiplexed? Okay, suppose 2 UVs want to do SRS. Okay, so there are multiple ways of doing this. So in the same cell, what might happen is if you are using the same cell is served by the same base station, 2 base stations, what will happen is these 2 UVs will be frequency offset. Okay, so I'm just going to go ahead and show one picture. Okay, so for example, this is density half, home 2. So one of the UVs will be sending the red and the other UV will be sending the yellow for that particular allocation. Okay, good. So no, but in a network, you don't only have one cell, you may have multiple cells. You have neighboring cells. One cell served by one base station, other cell served by other base station. Okay, so what might happen? So let's assume, just for simplicity, that this is one cell, one UV of one cell is the UV of another cell. Okay, the UV of the first cell is transmitting in the red, and the UV of in the second cell is also transmitting in the red. Okay, these 2 cells don't have any coordination; they're not uncoordinated. Okay, then what will happen? This will start interfering with the red. This red will start interfering with the red of this. Yes. So one way of decreasing this interference in some stage, averaging out this interference when things are coming from multiple points, is to make sure. So if you choose the same SRS sequence across the two cells, what will happen? These both will start interfering. Okay. So they want to reduce this interference by the process of averaging. So what they do is, you choose a sequence here, you choose a completely different sequence here in the next cell. Okay. So how does this happen? So they have a concept of group in an SRS. Okay. So you see this Rn is the SRS sequence indexed by U and V. So you choose a group. In that group, you choose a particular SRS sequence of a given length. Okay. So what they do is, there are two modes of operation. One is called the group hopping, or there is no group hopping. Okay. When you don't enable the group hopping, this FGH is a function that, you see, FGH is a function of the OFDM symbol number and the slot number. Okay, so this becomes 0.
NSF is what, sir? N mu SF. That is number of.
The slot number, sir. This is slot number. Slot number in a frame.
Okay, slot number in a frame, and this is the symbol length. L dash is the symbol length.
L dash is the symbol index. Yeah. Which symbol are you transmitting? Okay. So this becomes 0. When you enable group hopping, what happens is, this function changes every time, depends every symbol and every slot, depending upon what is the particular slot number and what is the particular symbol number. You choose this thing based on this particular complicated function. C is some random sequence. Okay, C is a pseudo random sequence that we have always used. In that, what they do is you can understand that this is C init of the sequence. This is the number of the index of that sequence. Okay, and then you do mod that. So you can understand this is a complicated function. One thing that just for now, what you have to keep track of is it's a function that depends on, it changes for every L dash and NSF. Is this clear? Okay, you always do mod 30 because there are only 30.
Not new parameters, sir. These are seeded.
Sorry?
L0 and M. These are the two new parameters which are.
M is in that this thing, sir. M is in the summation.
Summation of M is the 0 to 7.
See, this C of I. C is the sequence. C is a binary sequence. Okay, C is a binary sequence. So based on this, you choose that particular sequence number and you do the summation and take mod 30. Okay, so we can try this out, sir. I will show you this. Maybe with the homework problem, I'll give you this. You can compute this. But now, what we think of this is changing every slot and symbol number. Okay, and then there's the sequence number selection. Okay, so if the length of the sequence is less than 60, there is nothing to select because there's only one sequence per group. Okay, if the number of sequence is greater than 60, there are two options. Either you enable, if you do neither or group hopping, you disable group sequence hopping. If you enable sequence hopping, then what you do is you again send the sequence V randomly based on L dash and slot number. L dash and slot number, you pick out that binary sequence 0 or 1, but particular number of the binary sequence. Okay. So this is how this particular sequence and SRS sequence and group number are selected. Okay, so now let us understand what is the length of the SRS sequences and other things, and let's discuss this. So once you make your sequence, you have to do the mapping. How do you do the mapping is what I'm going to tell you. Okay. The length of the SRS sequence is given by this particular formula. Okay, NSRB is the number of subcarriers by RB. KTC, remember, KTC is either 2 or 4, depending upon whether you do comb 2 or comb 4. MBSRS is something that you select from a table. Okay, MBSRS is something that you select for a table. Okay, so what is this? Okay, so effectively, this MBSRS is nothing but the number of resource blocks in which you want to send your SRS. Okay, so the minimum number of resource blocks you can send your SRS is 4, and the maximum you can send is 272 resource blocks you can send. Fine. So now think of this. You have a UV. The base station is the one who commands, tells you what to measure. Okay, it's not the UV generally the sense SRS. Okay, the base station tells the UV, I want to measure. So okay, let's step back a minute. Let's understand this is kind of important. Let me just switch on my iPad. Okay. So this is your entire frequency. Let's say assume 100 megahertz. Okay. In this, a UV might have a bandwidth part. For example, a UV will say that I can support this 20 megahertz. Okay, this is bandwidth part. Okay. Similarly, next UV or other UV, there may be one more UV. This is UV1. This is UV2, which can support 20 megahertz. There is a UV3 which can support this 20 megahertz. Maybe I'm just giving some examples. Okay. Okay, this is UV3. Okay, maybe this is 50 megahertz. Okay. Okay. So now, what does the base station want to do? Why do you transmit SRS? You transmit SRS so that the base station can understand in which frequency it can. One of the reasons why you transmit SRS is in which frequency can it allocate you resources in the uplink. Okay. Okay. So, for example, so to understand that, what should the base station do? The base station should know the channel across this entire frequency band. Because similarly, the base station should know the channel across all this frequency, across this frequency band, Okay. So one thing it can do is it can put an SRS for all the 20 megahertz. Okay. So, but you should remember, uplink. Can you please switch off mute your mic, please? I don't know who it is. In the uplink, what might happen? See, uplink, you are power limited. You can only transmit 23 dBm average power. Okay, that's the spec. That's the standard across most of the countries in the world. Okay, so when you are transmitting only 23 dBm spread around 20 megahertz, what might happen? The power density across each subcarrier will be very, very less because you're spreading 23 dBm across 20 megahertz. Okay. So, for example, it will be, it's going to be very, very low. Okay. So, what the base station can do is, the base station, while you UV can support the entire thing, the base station can tell, I want SRS to be transmitted only for this part. For this particular UV at that point, instead of overlapping, it can say, I want SRS at this point. For this UV, it can tell, I want SRS at this point. It's up to the base station. It can tell. The UV did not send SRS for the entire band. It can tell the UV, I want for this particular 5 megahertz, I want to transmit uplink pilots. Okay, so that I can estimate my CSIRs. Okay, so instead of this, the UV might already know, UV might have already known this. So the UV might send for the UV2, you transmit SRS in this. Okay, so then what will it do? It will do some frequency division multiplexing or time division multiplexing so that these two UVs won't overlap in the SRS domain. Did you understand this? Okay, so there's an option for the UV. Either it can measure very, very wide band SRS. Then what happens? Then the power per element RE will become low, or it can go do multiple short measurements. It can do measurement at this point now, and the next time instant it can do measurement at this, and the next time instant it can do measurement at this. Okay, but there's a danger that as the time increases, this old measurement may become obsolete. Fine. So it's up to the base station to decide all this. So the spec provides us enough flexibility to do all this. Did you understand this? Any questions? Okay. So now let's come back to this. So you can see
one question. This is VK. Actually, good morning. Actually, in the bandwidth part, suppose the part of the supposing for UE1, this is good. This is evaluated good signal by the base station. At the same time, suppose for UE2 also the same part is the best. same part is the best. In that case, the conflict will be there.
So then what will happen is it will do TDM, sir. It will one slot it will do UE1, one slot can do UE2.
Okay, such type of.
The base station scheduler has to make this choice.
Oh.
Okay, or it may do multi-user MIMO across these two. It's up to the base station what it wants to do. Okay, so in general, what happens is a base station generally has a lot of UEs. It's not one, two. I mean, you can think of like hundreds of UEs will be there to choose from. Okay, so even if there are two UEs like this, it can find a UE3 which is overlapping with this, and it can nicely transmit that. Okay, so there are some theoretical results also which show that as the number of UEs become larger and larger, the scheduling becomes easier for the base station. Of course, it's computationally complicated, more complicated, but it can find a better optimal solution that way. But if there are only two UEs or three UEs, then what might happen is all the three UEs might have the same frequency, which is very good. Then it becomes a little bit more problematic. Then the rate of the system will automatically come down. You can understand, huh? Because you have to serve first UE1, then the UE2, UE3.
Thank you.
So if you look at this, so there are this is a table. This is a big table. I just truncated. I put 4 and 5 to 60. I did not put. There's a big table. Okay. So what this says is so essentially the base station specifies something called CSRS, BSRS. Okay. So if you look at the IAs, it says you can see CSRS and BSRS. CSRS is integer from 0 to 63. BSRS is an integer from 0 to 3. Okay. Okay. So 1 minute. Okay. Let's look at this. This is better. Okay. So CSRS and BSRS. So you can choose, the base station chooses one of the row, and they choose one of the column, and from there you get this MSRS. Essentially, this MSRS tells you what is the length of the number of RBs that you have to populate your SRS for. Okay. And one thing you observe is BSRS is equal to 0 corresponds to the highest bandwidth. BSRS equal to 3 corresponds to generally lower bandwidth. Okay, that's what happens. Okay. And this N0s and N1s and N2 and 3, N0, N1, N2, and 3 are some offsets in the frequency domain. Anyway, we are not going to go into that thing. The most important thing that you have to recognize is BSRS3 is a smaller bandwidth compared to BSRS2, BSRS1, and BSRS0. Okay. Okay. So this is what I was telling you. So larger bandwidth implies lower power density for larger distances. Okay, so sometimes it may be useful to transmit some smaller bandwidth. So for example, instead of transmitting 128 RB SRS, it may be good to transmit 64 SRS twice. Okay, when you do the 64 SRS twice, you can also multiplex 2 UEs. So you can do first half one UE, second half 1 UE, and then switch them over. Okay. But the problem with this multiple SRS transmissions over time is channel may change as time progresses. So you have to keep, the base station has to keep track of that one too. So this is called, so channel changing over time is called channel aging. Okay, this is a technical term for this. It's called channel aging. If you look at papers, they call it channel aging.
Even in short span of the time, this is channel aging.
No, in short duration it won't change, sir. So, but remember, okay, let's think about this. What is the most popular TDD structure that's used in the industry is something called DDD-SU. 3 downlink slots, 1 transition slot, and 1 uplink slot. Okay, so once you finish an uplink slot, you have to wait 3 more slots to get your uplink slot. 4 more slots to get your uplink slot. Almost.
Right.
Okay, so there's a gap. It depends on your TDD structure also. So it's not such a straightforward thing. So it depends on your TDD structure also. So you should also consider that before you can do smaller bandwidth SRS.
Yes, in some of the cases, the downlink, I think time slot, and that varies. Uplink that varies.
Yeah.
Long span is there. So
but instead of that, if you have 12 downlink, 1 uplink, 1 change, and 7 SRS, 7 uplink, then maybe you can do a little bit faster. It depends on how you are. So the TED structure plays a very critical role in all this.
So for each configuration, we can have different such type of arrangement.
Yeah. So generally, yes, sir. Yes, sir. So that is the reason why they are a little bit hesitant to change the TD structure too much for every slot. Okay, because a lot of these things are tied in very much to the TD structure.
Thank you.
Okay. So there's something called frequency hopping also. Okay. So what happens in frequency hopping? So you want to transmit 20 megahertz bandwidth, SRS, for example. What they do is they transmit first time, they transmit, they ran. So suppose you want to do 20 megahertz, out of that you will do, okay, let's take a more concrete example. Suppose your total bandwidth occupies 128 bit, 128 length SRS. Okay. So instead of that, you want to transmit 32 length SRS over 4 times. What they do is they want to multiplex multiple users also. So they do frequency hopping. So instead of transmitting the first 32 at the starting point, they transmit the first 32 in the somewhere in the middle, the frequency gap. And then the next slot, they hop it all around. They hop it so that the entire frequency is covered. That's called frequency hopping. Okay. So there's a parameter called B hop. Okay. So there's a complicated relation how you do frequency hopping. When B hop is greater than BSRS, there is no hopping. When B hop is less than BSRS, there is frequency hopping. Okay. So the amount of frequency hopping you can do and all that also, there are equations which tell you how much amount of frequency hopping you can do. Okay. But one thing you should remember is frequency hopping is also allowed. Okay. This frequency hopping again decreases the interference that is present in the system. It has its own advantages, but it's also complicated to implement. Okay. So all I want you to remember is that there is frequency hopping in SRS. Okay. So with that, let's look at a few examples and then we'll close SRS. Okay. So SRS, sorry. So this is a density half SRS. This is density 1/4 SRS. KTS equal to 4. Okay. This is an SRS that spans 2 symbols. So when group hopping is disabled, and symbol and sequence hopping is disabled, the same sequence is transmitted on both the symbols. Okay, the same. If the hopping is enabled, then the sequence that's transmitted here is different from the sequence that's transmitted here and from the here and here. Okay, again, I told you, because the group and the sequence number may change with respect to the symbol. This is SRS multiplexing. Okay, with density half, you can multiplex 2 different UVs. This is how you can multiplex. Okay, that's obvious. With density 1/4, you can multiplex 4 SRS symbols, 4 UVs. Okay. So all I want you to remember, so these are the main takeaway points from SRS. SRS are uplink pilots. They are mainly used to measure channel state information. And SRS are based on Z-OSU sequences. Different ports have different ports have cyclic shifts of the same Z-OSU sequences. Okay, and there are two different combs for SRS. One is called the density half, and the density 1/4. And based on that, you can also multiplex different users in the SRS. Okay, so this is all. I mean, that's all is required to understand from SRS at this point. Okay. Those of you who are interested should understand how you can decode SRS to obtain your channel estimates. Okay, that's kind of an interesting thing. I'm not going to teach that in this class. Those of you interested should look at how you can use the SRS structure to decode multi-port channel information. Okay. With this, I'll stop SRS. Let's get into the downlink control. But today, instead of going to the slides, I want to discuss something about the downlink control. Okay, let's discuss this using a pen and a paper, because this is one of the most important channels in the whole system. Without this, nothing works. Downlink control. Okay. So what is the downlink control channel? Okay, forget about the more standard things, but let's understand this. Okay. So downlink control channel is the control channel which tells the UV which tells the set all the UAs actually, are you scheduled for the downlink? Means so every slot has its downlink control information. Okay, think of this. So in that slot, UAs don't know whether there's information for the particular UA in that slot or not. That is one issue. The second issue, it does not know if there is information where it is. Okay. Okay, so the downlink control information has to tell the UAs a lot of stuff. Okay, one is a UV scheduled? 2. If so, where? 3. If so, what modulation? What modulation / coding rate? Okay. 4. MIMO layers. So I mean, I'm just putting some information. There are more other, a lot of other information. So okay, at least this is very obvious that at least this part.
I think format should also be written here. What? If so, where? If so, what should be the format of the information? Of the information.
Yeah, that is modulation and coding.
Okay.
So
this includes.
Yeah, this is a modulation and coding. Okay. So, but there's a problem here. Okay. So the base station, at this point, the UV doesn't know whether it's scheduled, nothing is known. Okay. So the base station has to transmit a bunch of information, and in the control channel, all the UVs will decode this control channel. Okay. And the UVs should understand whether that information belongs to them or not. Okay, that's one issue. Okay. A second thing is the same downlink control channel information is also used to broadcast information for a set of UVs. Okay. Yes, now for example, chord set 0 we saw slip 1 message. Okay. That should be able. Such kind of broadcast information should be decodable by all the users. Agree? It's not UV specific. There will be some information like this. Okay. So the question is, how do we enable that? How do we design this control channel information? How do we design this control channel? One, so that some information is very specific to UV. Only particular UV should be able to decode. If other UVs decode, then what will happen is one is of course security is an issue. Another thing is the other UVs can pick up that this is my data, and they will try to do something, and the whole system will go for a toss. Okay. And second thing is there should be a provision so that say a set of UVs or all the UVs in the base station can decode some set of information. Okay. Okay. This is one issue. The second issue is, if control channel is very important, if a particular UV is not able to decode control channel, it will never be able to decode the data channel. Why? Because it does not know where its data is. Okay. So in general, one thing is very obvious. Control channel should have a lot more redundancy compared to data channel. It should be more highly protected compared to data channel. Yes. Okay, the simple reason is if the control channel is not able to decode, the whole slot will go for a base for that particular UV. Okay? So the UVs even at the cell edge should be able to decode this control channel. Okay. So if you are sending so essentially what is going to happen? You're going to have multiple UVs. You have to send control information for example, 2 UVs. One UV which is close to the base station, another UV which is far from the base station. Okay. So the control channel design should have a provision in which you can put a lower, maybe the same amount of information has to go to both. Okay, maybe the same amount of information has to go to both, but the UV which is farther away should have a lower coding rate. That means that the same information will be spread over more number of bits compared to the UV which is closer. Okay, so this provision also should be built up into the downlink control channel. Okay. And the most important thing is, how do you tell the UVs? So control channel is also like any other channel. It will get decoded, and UVs have to pick out the correct information. How will the UVs know whether the control information is for them, and if so, which parts of the control channel is its information present in? You cannot put one more control channel for that. That's not possible. It does not make sense. Okay. So you are understanding that the control channel is a little bit more complicated than the data channel, okay, because of all these aspects. So what we are going to do is we are going to understand how these different issues are addressed in the in the 5G NR control channel. I mean, the similar issues happen in LTE also, but the control channel is similar to what is there in LTE, but there are differences. So I'll point them out to you. But these are the main issues that have to be addressed. So effectively, there's something called blind decoding happens by the UAs. Okay, the UAs, we have to figure out how to do this in such that UAs can understand where its information about the control is, and they are decoded by the correct UAs. Okay. Any questions or any discussion? Let's discuss this today. And the next class, I'm going to start the control channel, downlink control channel. Any questions? Okay. So control channel. So we are going to look at the downlink control channel. So as I said, downlink control channel, transmission of control information. What is the control information generally transmit? It transmits scheduling grants. Essentially, this tells the UEs that UE is allocated, UE is allowed to transmit in the uplink or the downlink. Okay. So PDCCH also contains information about the uplink grants also. Okay. So the downlink control channel will also have information of the uplink grants, and it will also have information about the downlink grants. Remember that. Okay. So it will have the information required to demodulate PDSCH. For example, what is the modulation, what is the code rate. Okay. It will have information about power control. It will have information about something called transport formats. I will tell you what are the transport formats in the next classes. Okay. So understand this PDCCH is a layer 1 control channel. Information does not come about this from the higher layers. There is control information, RRC control information and MAC control information that flows in from the higher layers, but that is generally sent in PDSCH. Okay, this PDCCH is mainly a control channel to demodulate and decode data. Okay, whereas the control information that flows in MAC and RRC parameters is to configure stuff, and that flows in PDSCH generally. Okay. I'm going to stop at this point. Okay, and next class we'll look at this. First thing we are going to answer the question is, how does a UE know if a particular, if it decodes the control channel, how does it know whether that information is meant for it or not? Okay, so there is some fundamental stuff that is done using CRC. I will explain you that in the next class. Okay, so tomorrow we are going to again meet from 10 to, tomorrow is 10 to 11, I think so, class. Okay, we'll meet at 10 to 11. Okay. So by the way, now that the students are not there, we can change the class timings if you want every day to 9 to 10. I will leave it to you, everyone. Okay. Otherwise, we can continue with the same thing. Either way, I'm fine.
Okay, so you can make it 9 to 10. No issue.